Okay, welcome to, what is it, lecture number 3 in the summer term 2025 on computer algebra systems. So, last time we used the Euler-Lagrange equation to get some simple ordinary differential equations, or maybe not so simple in general, for one-point system, and solve this. The beauty of this method is that because it starts off with energy, and energy is a scalar thing, you can dump in, a lot of as many degrees of freedom as you wish. So, and now today we go from what we had with one point. We showed that we can do this with many points, and that this is essentially the same thing. Yeah. So, unfortunately, nothing new today. Yeah. So you came out of bed for nothing. So that it's not completely nothing. I'll do a little bit of Mathematica stuff in between. It's a Mathematica lecture. So Mathematica is very often also used for its visualization properties, obviously, to make the things that you want to study also visible. And if you remember last week we had, was it last week? Or was the Easter week? I don't know. The last time we had this mass spring model, where we just had one point and then a line, and if we want to have a rendering that looks more fancy, we would need to draw a spring, right? So, and now let us think how we in Mathematica would do this. So a spring, in essence, would be a spiral, that can be imagined like this. So you have you have in the normal plane, you have a what is a circle function that you can write as a sine and a cosine. You have problem seeing?
Yes, I forgot my class, but with this.
You forgot. Should I don't know. Okay, so you optical. Okay, this is. Do you want to have a piece of paper and make a small hole? Yeah. Okay, you see, I don't.
It's fine, thank you.
Okay, so now we're cutting off a little bit of this. I hope. Yes, so we have a circle which we can write as a sine and a cosine, and in between, and this goes along the say what we have here, the x-axis is just a linear function, right? So, and then we can put this into a parametric function, so one point in 3 dimensions, and do this and put a parametric plot that we plot from 0 to 1. And in this, we have to specify 2 pi tt, so when tt goes from 0 to 1, we'll have to say how many times do we turn around, so this is the number of turns. So if I put, now this is the beauty of this, if I had this in PowerPoint or something, then I could not change it. So one turn would be, of course, turns around once, and we can also see how this looks like when we do it. Okay, then we get actually a Moiré picture. Do you know what a Moiré picture is? No, this is, you see these So these lines that you see here, they are not part of the plot. This is when the lines that are crossing, yeah, just have in. You see, if I put my fingers, yeah, so they look broader because they are overlapping lines. So you have the cases where you know they are completely aligned, yeah, where you can look through, and then where they are completely misaligned, and this is, you know, depending on the position. Actually, this even has so I mean I'm digressing, but for example, because I'm actually a semiconductor guy. So when you put so just as an application of this, yeah. So if you put semiconductor, if you build semiconductors, you'll have to do some photolithography. So when you define the structures with light, actually, yeah, and then you have several layers of this, and then you have to put these layers on top of each other, yeah, and then you have some what you can do to make the alignment, yeah, is you put some lines somewhere on both of them, and then you can see according to the structure of this how they interfere with each other, whether they are aligned or misaligned, because you have to you need to be in the nanometer alignment range there, yeah. So this is when you have here many of these lines. But okay, this is not what we are going to talk about today. This is also why okay. So another thing is newscasters on television, they are not allowed to wear skirts or ties with where they have lines on it, yeah, because these lines interfere with the matrix of the camera, yeah, and then you see these moire structures. Yeah, this is typical, and this is what we saw here, yeah. So this is like taking a picture, and there is this interference. Okay, we see we had a holiday. Let's think about the following. I mean, we made this spiral, but we made the spiral along a certain axis, yeah? And of course, if we want to have a spring, we have to put the spiral along an arbitrary vector, like we have here. So actually, since I made it larger, should I make it smaller again? That we have, or how do you like it?
Yeah, smaller is fine.
Smaller is fine, because I potentially don't get everything on the screen now. Yes. Okay, so we have this in an x-word pointing vector, but we'll want to have this in an arbitrary vector, and for this we'll have to define this along some axis. So first we have to be able to actually describe. So what do we need? We need a vector along which we want to have it, and then we need the two orthogonal vectors, yeah, for the plane in which it will turn. So we have the normal to the plane, and then we need the other vector. So how do we get the other vectors? Well, the other vectors are orthogonal, and now we use this orthogonality to actually derive them. What do we know about orthogonality? We know that when we take a scalar product of a vector with a vector that is orthogonal to it, then we'll end up with 0, right? So what we now can do, we take the vector of our coordinate system x, y, and z and do a scalar product. So in a scalar product in Mathematica, it's just putting a dot in between the two vectors. Yeah? So this is how we get it. So now, and we put this to 0. So this is one condition. So this condition is not enough because we have three values here, and we have only one condition. So we need two more conditions. What else can we say as a condition for a unit vector in an orthogonal way? So orthogonality we have defined, yeah? So now next thing, it should be a basis, so it should be a unit vector. So unit vector means it has unit length, and unit length we get by having the scalar product of the vector itself with itself being 1. Yeah? Then it's unit. So, okay. So we have now two conditions. There's still something missing because we'll have we need three conditions to make this actually solvable. And now obviously we are stuck because there is nothing unique anymore. Yeah? Because you have an entire plane, yeah, and now you could have any vector in that plane. Obviously would be a potential basis. Yeah? So you simply have to make a choice, and this choice may be a bad choice. Okay, coming to the bad choice later, but let's make a choice, and the choice that we make is simply that we assume that also x is 0. Yeah? So that we have an additional constraint. Yeah? So this is just a choice. Okay, now we have our conditions that should give us an orthogonal vector. And the way we do this in Mathematica is we say solve, we give the conditions, condition for orthogonality, condition for unit length, and assuming also x equal to 0, and we solve this to ortho x, ortho y, and ortho z. So obviously this will give us ortho x equals to 0. Yeah, because this was the assumption. And otherwise, we have these two opposing options, yeah, because obviously that would be true for vector going that way and going exactly the opposite way. So of these two, we have to choose then one. So, and so we need a basis. So once we picked one, we get the other one by taking, okay, so the other one needs to be orthogonal to both of them. Yeah? And the simplest way to do this is to take the scalar product of the two, yeah, and get a vector out, and this vector will be orthogonal of the two of them. It will not necessarily be unit length. Obviously, this is why we have to divide by its length, and its length is, of course, the square root of its square, so the scalar product with itself, which we just learned how to do this. So, now, is this a good thing? You may say in principle yes, but there can be a problem because this thing here may be 0. Yeah? that is that we assumed that Vx is equal to 0. No, this is the orthogonality. Wait. What did I wrote? Now we have two vectors, but the problem is that they do not exist if y and v sets are simultaneously 0. And this is due to our assumption order x is equal to 0. So in this case, we have to choose a different set of vectors, and we can simply, do this here by overloading. So if our vector is just Vx, for that particular case, and the others are 0, we'll fix this design like this, and otherwise we use the result that we had above. Okay, I later think whether this is necessary or whether I made here a mistake, but this is not the point. The point that I wanted to make is just, okay, you can overloading, to use this. So now you can define your spiral like this, and here we use a function definition. And you see how flexible Mathematica is in taking its arguments. So you can take these arguments in different ways. So you could take the entire vector, but you can also split up the vector like this here. So we'll take a vector, but we're already in our patterns, that's the word I was looking for, the patterns, that we put here is we take the values out of the vector already, so this is the x1 pattern, so we have this underscore is the first part of this vector, and now this function will accept arguments only if there is a vector of 3 first and a vector of 3 second, and then we have t, w, and n. So these two are the first vectors. Then t is so t basically is the coordinate along the vector axis. W is the width of, how wide are the spirals, and n is the number of terms. So, and then do you remember what we said about module?
About the list.
No. So what is module doing? Okay, no, you don't. From memory, what is module? What is module doing in Mathematica?
I don't remember.
You don't remember. So we make a scope. Do you remember what a scope is? Yeah. So how do we? So we make a scope, and inside the scope, so this first argument that we have here is the list of local variables that are scoped. So they disappear. So we'll define them here, and they will disappear later. So, and now what we are doing is we take the end vector and minus the start vector. this is like we are shifting the vector, so we are putting ourselves in the coordinate system of the starting point here, right? Then we compute the orthogonal vectors by the function that we just defined, also vector orthogonal, yeah. And then we return. So this is the return value of this function. We return the spiral, and we shift it. We shift its starting point to the starting point of this to point number 1. Yeah. So that it will start from point number 1 and go to point number 2.
Okay.
Yeah?
Mm-hmm.
So then we end up with this here. So spiral 1, so we say from 0, 0 to 1, 3, 3. But we don't need to start from 0. Yeah, we can also start from somewhere else. Okay, so the parametric plot will automatically arrange the the range that it shows. So this is why it's not very obvious when I change this. Yeah, so you only see. I mean, you can read it from the axis if you read here the. I don't particularly like the way this works, because when I leave it. Okay, anyway, yeah, you can read from the axis maybe the positions where you are, and then you have your spiral. Okay, spiral is not yet very good approximation of a spring, because a spring usually has an end point that goes to the center and the beginning point that also goes to the center. Yeah. So now this is your personal creativity, how you would like to do this, to draw this. The way I suggested to draw this is using a small percentage of 10% of the range where it gets smaller and when it's at the two ends. Yeah. So, and this I decided for no particular reason at all to go with the forced power. Yeah, of t. Yeah. So the only thing that we want to, so you see, you have to multiply this by 10 by the power of 4, yeah, because this is 0.1 by 4, so that the two pieces match up. So it's t 0.1. Yeah, so that should be 1. And at t equal to 0.9, it also should be 1.
Yes.
So that when I define a piecewise function, that is a function, yeah, in this with these three cases, this will be continuous still. Yeah. So, okay, when I do this and compare the two, yeah, we'll have here just the normal spiral, and here something that we could approximate as a spring. Yeah. So, but this is art, not science. So, and then we want to attach a bead to the end. So I have a position of the bead. Position of the bead obviously is the end of the spring. So we have a position of the origin, position of a bead. Then we have a radius of the bead, and then we can draw spring to bead, position of origin, position of bead. Yeah, and then we can generate a graphics of both of them, of a sphere, position or beat with the radius. So we make a sphere and we add those parametric plots, both of them together in one graphics, and then we also show it. And then we have this picture here. And now, so this didn't have anything to do with partial differential equations so far. Now going back to our Euler-Lagrange thing from last week, so this is again nothing new. We take the kinetic energy T and the potential energy that we had. So there's a gravitational potential energy and there is a spring potential energy. Yeah. So the difference always, I always say in school, they conveniently always put the origin of the coordinate system in the non-elongated position. In the equilibrium position, they put the origin of the coordinate system, usually, yeah? And this actually, this is also what the mechanics guys that are just one floor above us here, they also like to do. Yeah. So we do this a little bit differently. So we have an arbitrary coordinate system, and we have to attach an equilibrium distance. Yeah. So there is a distance for which there is no force in the spring, and both when you elongate it or when you compress it, you'll get the force. So this is why we have this D here. This is the equilibrium elongation. Yeah. Good. And the square root of the difference between position 1 and position 2 obviously is the length between them. So assuming no dissipation, this is why xc is 0, and then we have 3 coordinates taking the Euler-Lagrange equation, giving us 3 ordinary differential equations that then we can solve with ND solve, given some parameters for the mass, spring constant and gravity. Yeah? Okay, so I think we've done this last week already, and now we can simply attach our picture here. Yeah, so same solution as last time. Yeah, in order, so we do an animate. We extract the coordinates here, and then we show the parametric plot. But what is important here is that we define the range. If we do not define the range, it will, compute the range all the time in each picture. So we'll always scale the thing. If we want to have a fixed range, we have to fix it by hand somehow. Yeah. So now I've fixed this by hand, and now you can see this moving. And by the way, I personally think this looks amazing, yeah, but of course this is a very simplified way. So one thing that we did not consider in this visualization is that when you elongate a spring, it will become more narrow because the length of the path will be conserved. Yeah. So now this we did not do here. We did not conserve the length of the path here. Yeah, but this, if you like to do it, now you know how you would do it. Yeah. Okay, so now all of this was a little bit to see what Mathematica can do. Now let's let's do actually the more interesting stuff, and just say we want to have two bodies attached, or we are, or not attached, I mean studying two bodies. So say we have two bodies, one with mass 1 and one with mass 2, and one with one position and one with the other position, or respectively their velocities. So then obviously, so now you see, this is the good thing, energy are scalars, and so if you have more bodies, you have more energy, you add up the energy of the one to the other, yeah? So you don't cut things somehow, how they are connected, yeah? That's not important, you sum up the energies. All, the only difference that we do here is that we have kinetic energy, so all kinetic energy goes in T and all potential energy goes in V. So now there are two types of potential energy. The gravitational field, so there's a position Z of the first particle and Z of the second particle. Yeah, and then there is there's the potential energy of the spring. And now here is the connection. Here comes actually the connection of the two bodies. And this, of course, depends on your arrangement of the system. Now, our assumption for the system, which I've not drawn, but we'll see it on the next slide, is we assume that the first spring that has the constant K1 is attached to a fixed point, like the ceiling or something, right? So this is the or you could say the origin of our coordinate system. And this has an equilibrium distance 1. So suppose one spring is not attached to a fixed point, but say to another point, just to the mass of the other point. So what would happen? Yeah. So you simply have the elongation of that spring. So you'll have one point, one end of the spring in one mass, and the other point on the other mass. So the elongation will be the difference between these coordinates. Yeah. So and then now this is the elongation, and this is the equilibrium minus the elongation minus the equilibrium elongation minus the elongation. Yeah, and just as a fun part is when this is now very, very long ago, when I first made this setup for when I started doing this lecture, one of the civil engineer colleagues came up and said, "So your result is wrong." And okay, I said, "This is the physically correct way. This is very strange that my result should be wrong." Yeah. So he should what he learned as a civil engineer and show me what is wrong. So now he wrote things down and said, now we have to take the reference configuration. Why do you need the reference configuration? Well, yeah, we have to, we have small derivation from the reference. Yeah, so this is how civil engineers think. Yeah, as I said, they have some reference, and then they say there's a small deviation out of this. Yeah, so they make a complicated simplification here, and I say, okay, now I know why you think my result is wrong, but your method is wrong. Yeah, I mean this here is exact. So there is no reason that the one point is somewhere close to the other point or something. This is simply That's simply the way it is. Yeah? And there is no reason to use a reference configuration in order for you to try to simplify something, because in my opinion, using a reference configuration makes everything more complicated. Maybe, just maybe you need to do a little bit less computation, but why you bother about computation? You have a computer, yeah? So, right, so no reference configuration here, yeah? So this is just the reality. So now we have put all the energies together, we get the Lagrangian, and now we have to take these, now we have 6 degrees of freedom, and now we have to solve for 6 degrees of freedom. So everything is the same, we just do it for more degrees of freedom. So we'll have to specify more initial conditions, yeah? We have to specify more parameters, like mass 1, mass 2, K1, K2, D1, you know, D2, yeah, all of that, and then we have to solve for all of them again. So, and now comes, you know, all of these solutions, which here Mathematica gives us a very small overview on how they are, how they behave. Yeah, so can see this here. So this is difficult to interpret, but this one here, if you just plot it, it's much more easy to actually interpret. Yes, it's the same data. And if you watch this, you observe that we did not do something specifically, namely we did not bother with collisions and exclusions from the spring. So we just draw the spring, but there is no physical spring that would give us a constraint that the two springs don't go through each other. Yeah? So when you observe this here moving, it looks very nice up to the point when the one spring goes through the other one, right? Because this is not included in the model, but it can also be included in the model. The problem then would be you have to go through all the points of the spring. But of course, Euler-Lagrange can do this, yeah? It depends on you. Okay. Now we had this without dissipation. Now let us add some dissipation. And today, last time we had friction in air as our dissipation. Such systems are usually have dissipation from more dissipation from a dashport perspective. Yeah. So if you have a real spring, also has some real dissipation, and this is modeled in technical mechanics as the dashport. Yeah. And this dashport can be modeled by this little bit strange looking energy here. So the energy, this actually looks like an energy stored in a spring. And yes, I have to apologize that this is potentially not the, okay, this is it's a potential energy, but it's potentially not the most intuitive way how to see this. So when you learned what you potentially learned in your physics class is that the dashport is the dashport force is a constant times the time derivative of the velocity of its velocity, right?
I never saw dashpot or the springs in this kind of.
Okay, but okay, you should have learned somewhere about a harmonic oscillator. Yes. So, for example, in lecture 1, this series, right? Mm-hmm. And there, you have the elongation of the spring x times, so what x times k, but what is actually x minus d times k, yeah, and then there is this the damping, which we call dashpot, is c times x dot.
Yes.
Yeah, so this you have C. Yeah, so and this is this force here, and you get a force by taking the time derivative of an energy, or you could also say you get the energy when you integrate a force, force times what is it, way. In German we say, or we always say, Arbeit ist Kraft mal Weg. Yeah? So actually is force integrated over distance applied. Yeah, is the energy. So the energy that corresponds to this force is actually related to the elongation squared times the constant. So, but you may be more familiar actually with this here than with that here. So, yeah, the point here, of course, is again that this is not the movement out of a reference configuration. Yeah. So this is how potentially civil engineers, where everything is moving just a little bit, they would now assume this is a elongation out of a reference configuration, but we don't need to use a reference configuration. It's the difference in velocities between the two endpoints of the dashpot attached, and the dashpot is attached to the spring. So again, it's the position 1 and position 2. Yeah. So we have here the difference of the energy of the velocities. Yeah. So if they if both ends of the dashpot have the same velocity, then there is no dissipation, obviously. Yeah. So it's only the difference. Okay. So now we can define our energies here, and because we said the dashpot is a part of a real spring, yeah, so they both have the same attachment. So the first one is attached to the origin, so the origin does not move, yeah, it would be constant. If we take the time derivative, it will disappear. And in the second case, we have the difference between these two positions. So we'll get a coupling between the two here, obviously. So then we'll define all our, for all coordinates, our dissipation. Yeah, so again, we'll have to take release, hold, some function. Okay, so that's because there is no derivative of t in this. This will not do anything in this case, but in case there would be, we should always do this. And then we take the derivative, and then we get our non-conservative forces that simply go into the Euler-Lagrange equations. Yeah. So now you don't need to think anymore. You just do. Now you'll have the same thing. You solve it. The only difference is that you also have to specify the dashpot constant. And you already see from this results here. So you remember previously we saw this erratic movement because there was no dissipation. Yeah, and here we have some dissipation, so everything is going is converging to a constant here. It's not necessarily, the constant is not necessarily 0. So you see, now this is the same example, and actually, it's pretty visible here that these 2 points down here, they are more or less synced, yeah. So they're after some time, the velocity difference between them is getting very small, yeah. So you see in the beginning there actually is some movement. Am I talking too quickly today? I don't know. Let's see. But I have the impression I'm talking extremely slow today. But okay, we'll see. Okay, clear, right? Any questions? No. So, then something new. Well, not extremely new, but see what we can do with this. So, one thing that can be studied very nicely with this is planetary motion. Yeah. So, because you could say that the heavenly bodies, if this is a word, they can be seen as particles with potential and kinetic energy. So it's a funny thing that things get simple when they are very small or when they are very large. Yeah, because the interna of a planet, they are pretty complicated to deal with. But you know, if you're far away, and then you can just say, so this is a mass point, and this is in a field, in an energy field. Let's just start with some streamlining of the notation. Yeah, because so far what we always had to do is to define all the 3 coordinates for all our mass points. Yeah. So you can imagine if you have many mass points, this is going to be annoying. So let's do this more like generic and define something P, and to make it nice, but this is absolutely not necessary. I put this arrow on top so that we can identify this as being a vector. Yeah. And now the nice thing in Mathematica is we can if this is useful for you, we can not only use in a function definition this excuse me? The pattern, yes. The pattern as an argument, but we can also use a pattern as an index. Yeah, so we define pattern as an index. You see, when we, for example, H, so how do we do this? Go to control underline, yeah. So we'll have some index and see, for example, you need to know how these things react. So for this, it uses an index not as a name but really as an index. Yeah. So for example, if I have hi, I can replace h by something, and you see we'll get something else with the same index. Yeah. And we can use patterns in this here also, where okay, well, what now? I have to think about an example. So No, sorry, no, this is of course nonsense. So say we want to replace okay, I'll repair it in a minute. So say we'll have this if I say is equal to 0, then it's A and otherwise it's B, right? So, and now I can have something like this. Yeah? So we can play with this around. Yeah. So it can sometimes be useful to do this. I mean, for your notation. So we'll have this here defined with an index so that we can count up our points. So we have point 1, 2, 3, yeah, and this will now give us, if we, I've unfortunately forgotten how to make this error. So there is, so what you can always do if you don't remember is you can go to palettes, yeah, and there would be, for example, a classroom. So then we can navigation, writing, formatting. Navigation is not what we are looking for. Keyboard typesetting. Okay, here you can go, right, when you don't know how to write the index, you can also use these things. And arc, basic, advanced, calculator. Writing and formatting. Okay, now this is the helps in settings. So okay, I've done this very long time ago, and I now forgot how to write this. This is, let me see, P control up is the wrong one. So you can also write an index with control up, or you can use, I should give you this as a homework to find this out. Navigation, writing, basic typesetting. Okay, so we need to put something on top of this P, and then there could be Vic. Right arrow. Okay, I was able to do it. Yeah. So you can put. Okay. So you need this one thing on top of each other, and then you can write escape, Vec, escape. Okay. Yeah. To actually do this, and here now obviously, so this is control underline 7, yeah. Now it gives me, why didn't it give me, okay. So, can you explain why it didn't give me what I wanted?
Probably because of the index, right?
No, not of the index, because I did not write t. This is always a function of t, okay? So, I mean, I can make it something else. I can make it a function of a, because we have a pattern here, yeah? So I can put this like this too, yeah? So, and now it will generate for me I'll have to get this out of the way because otherwise. Okay, now for making vectors. Now the one place where we had a very simple, very strong simplification was in the potential energy in the gravitational field, because we simply said that it's the height, that is the height, yeah, times the mass times g, and this is of course not this is a very strong simplification. The real gravitational force works like this. There are two masses. There's a symmetric force. Yeah, there are two masses multiplied with each other, and then there is the universal gravitational constant. So the potential energy is minus this constant times the product of these two masses divided by the distance between the two bodies. This is the energy. Yeah. So, and well, the kinetic energy now can be written like this. We have the positions. We take the time derivative, so we have the velocity, and then we do a scalar product with itself. Yeah, and here we define two bodies now, m1, m2, and m1, m2. Both of them have kinetic energy. So then, with regard to the dissipation, we usually assume that in outer space there will be not a lot of dissipation. Actually, the dissipation that we observe, so we first of all, the dissipation is slow. So on the time scales we are interested in, we see very little dissipation, but we see the effect of dissipation. Do you know where we see the effect of dissipation in for example, Earth-Moon system? Okay, maybe dissipation is not the... Okay. So where is most dissipation going on? Well, when you have Moon and Earth, yeah.
Okay.
So then, they turn around, and they have internal dissipation. Maybe on Moon and Earth it's not so obvious. There is one, I don't know how familiar you are with these things, but there is one moon in Jupiter where it's pretty obvious. So this is the moon Io. Yeah? So the moon Io is very close to Jupiter, and it is on the other side, there is a moon that's called Europa. Yeah, that is also pretty close. And then there are two more further outside. And this moon Io has many volcanoes. So there's a lot of heat going on. Usually the small moons are usually pretty inactive, yeah, because they're internally, because they have their surface to volume ratio is unfavorable to keep a lot of heat inside. Yeah, so they cool down quickly. So they are usually, like our moon is a cold place. There are no volcanoes on our moon. Yeah, but on this moon there are a lot of volcanoes. And another moon that has volcanoes is this Enceladus in Saturn, but it has ice geysers. Yeah. So the reason why these things are so active is because there are other moons, and together with Jupiter, for example, so Europa and Jupiter, so they tear on that moon, so they deform this, and inside you have this dissipation, and this is heating the sky up. Yeah. So this is where dissipation happens. So it's not that dissipation does not happen, but it is a special cases. And usually we also have so in the Earth's moon system we also see dissipation, but this dissipation happens more almost exclusively on Earth, not on the moon. Yeah, and this is inside the title. These are the tidal forces that cause dissipation on Earth, not on the moon, because the moon. So from the perspective of the Earth, the moon is always in a different position, so it's tearing on the Earth. But according to the moon, the Earth is always in the same position. So the moon, the Earth does not tear a lot on the moon. Yeah.
So in the end, it's heat, but this heat is.
So this heat will, yeah. So the heat. Okay, the heat will be then inside, will keep inside the body. The reason why we don't, from this outward perspective, we don't need to care about this is because momentum would still be conserved. Yeah, and the one thing that they exchange is angular momentum. Yeah, so the entire thing is conserved with angular momentum. So the move, okay, there's one thing that is of importance for here is actually the position of these moons are shifted due to the exchange of angular momentum. Yeah, because we or you could say the rotational energy. I mean, if it was okay, it cannot everything be dissipated, because in addition to energy that may go to heat, we have momentum and angular momentum. Yeah, and the angular momentum is conserved, but it can be transferred from one body to another body. And now there are now two cases with moons, namely when they turn in the same direction, if they rotate in the same direction as the planet rotates. So then the deformation of the planet lacks. So because the planet usually rotates faster, so then the deformation of the planet that rotates faster is moving ahead of the moon.
Okay.
Yeah, and because it's going ahead of the moon, so the transfer of angular momentum is from the planet to the moon.
Mm-hmm.
And then this means that the moon has the moon's trajectory has increasing amount of angular momentum, which means that energy is transferred towards the moon, and in order to compensate this, it moves further out.
Okay.
While when the planet and the moon have opposite moving directions, then the deformation is lagging behind the moon, and the moon is slowed down, and the angular momentum of the moon's trajectory is transferred to the planet. and the planet and the moon is going down.
Mm-hmm.
Yeah. So this is why this system is unstable and the other one is stable, and this is why almost all the moons that we know of rotate in the same direction as their planets. Yeah. There is one moon of what is it, of Neptune, Triton, that rotates the opposite way. Yeah. Why are we talking about this? Okay, we want to see a little bit about planets. It's Friday. Okay, so we simply do the get the Euler-Lagrange equation, and now comes actually some Mathematica in here. So we don't want to write all of them down point by point. So what I'm doing here is I want to get all the equations in one go. And I've defined here the Euler-Lagrange equation, taking in L and taking its coordinates. Yeah? Very simple. And then I apply this to all my coordinates that I have. So how do I do this? So fancy Mathematica, this is kind of functional programming, if you will. Yeah? So this end here, I don't know why this is called end, yeah, but this is what they call is a generic function, yeah. So say let us try this. Say I think, okay, I take this times 5, and I say end okay, now I'm making him, now we'll see that I'm not well prepared. Let me see, U, does it do it? No, sorry. Okay, sorry, I'm always kind of a little bit confused with this myself. So this, okay, let's okay, the thing is, there is something that's called map, and map is a function that is used on lists, yeah, to apply a function to all elements of a list. So then we need to have, say we have the sine function, yeah, and we want to apply this to a list A, B, C, okay? A, B, comma, C. So we get sine A, B, C, right? So now sometimes I want to apply here a function that I mean, define myself, yeah? But sometimes also I want to apply a function that I don't want to define. It's like a lambda function. Like a lambda function. Not like a lambda function, but a lambda function, yeah? So, and this I can do now in, say, I define my function 7 times, you know, the argument. Yeah? So, and then I have to tell them that okay, we don't write lambda, but we write end. I don't know why they use end. Yeah? So, now this is the lambda function. Yeah? Okay, so this can be, this doesn't need to use a map. Yeah, that's just here I define I have an ad hoc function. So this is not only for map, but this can be used wherever I have some you know, where I have to take, where there's a function that takes a function as an argument, yeah? So, now this is exactly what I'm doing. I'm taking the map, Euler-Lagrangian, and then I apply this to all the coordinates. So my coordinates are inside a vector, yeah? So we'll have now, we actually have a list of different vectors, and this is a list with, you know, a recursive list, if you will. So there are lists in lists, and but I wanted to for every coordinate itself, and to flatten a list of lists, we can use the function flatten. Yeah, so this will give us all the components inside these recursive lists in just as in one list. Yeah? So then we get all the coordinates out, so we'll apply the Euler-Lagrange equation to all the different coordinates that we have here. And then we get out these six partial differential equations. Yeah? So we do this only once, and we have 6 partial differential equations. So now if we want then to solve them, we of course have to specify, so we'll have the equations of motion. Okay, so we have to do several things. Now we have a list of these equations of motions, but we have to attach initial and boundary conditions to them. There are no boundary conditions, sorry. In this case, there are no boundary conditions, but initial conditions. Yeah. And so we put a new list starting with the list of partial differential equations, and here the initial conditions. So now the initial conditions is I put Earth, yeah, I put Earth at the position 0, 0, 0, and I put the moon in a distance. Sorry. No, this is not the position. This is the time derivative. So this is I put Earth at velocity 0, right? And I put the moon as 1020 meters per second. Yeah? And then I put the Earth at position 0 and the moon at position 0.4 billion meters away. And then I add the mass of Earth and the mass of, I do the substitution of the mass of Earth and the mass of the moon. So I have to, because this is again a list in the list, I have to flatten this. And I also have to flatten that one here. And I hope you see how I did this. I said that the velocity is in y direction and the position is in x direction. So that velocity and position are orthogonal to each other, right? Because if the moon is now like this, then it's moving straight in this direction, right? Yes. And then I solved this for, so the rotation time, so a month is 27 days, basically, times 24 hours times 60 minutes times 60 seconds times 3 months. So I'm simulating for 3 months, yeah? What you notice, it's not exactly 27 days apparently. So we get 3 humps, but it's not exactly matching up. Yeah, Yeah. So, but you see, it's roughly the right time. One thing that you see with what you see with Earth is wobbling around. Yeah. Of course, the moon is wobbling around too. The set position is always flat. Yeah. Nothing happens. So this is the plane of the solar system, if you will. Yeah. So this is always flat, and you see that the Earth is a little bit moving, apparently. Yeah. So let's see whether we'll see this. You see, these are the 3 rotations. The 3 months that we are looking at, and you see that everything is shifting a little bit because the entire system is moving. Why is the entire system moving?
Or it would be towards, it would be attracting towards the moon is attracted towards the Earth, right?
The moon is attracted towards the
So
Earth, but
the
it's...
thing is that the moon
Yeah.
would be going closer to the Earth. So it's shifting.
So why is the moon going closer? I mean, I just spent. So we just talked about what the moon is doing, but there's no internal decrease of freedom. Why would the moon go closer to the Earth?
Well, because you get these equations, and the thing, if I understand, we would need more to make it stable so that it stays in the same place. We would need to consider other. So in the end, to answer your question, why is it moving? I would suppose that because it's not a stable system.
Oh my God! Earth and moon are not a stable system.
Okay. Yes.
I mean, like there have been. Okay. Yeah, there is some. I think they won't last forever.
Mm-hmm.
But they have been together for quite some time.
Okay, yes, now I understand, yes. But the shift that we're seeing. Okay, no.
Okay, why do we have some shifts? I mean, there's a very simple reason for this. I mean, so when we set here the initial conditions, when we set the velocity of Earth is 0 and the velocity of moon is non-zero.
The velocity of Earth is 0.
Yes.
And the velocity of the moon is non-zero.
Yes.
Mm-hmm.
Then we have a finite, then the momentum of the entire system is non-zero,
Mm-hmm.
right?
Yes.
So then the entire system has to move.
Okay, yes.
Yeah, so actually, if you want to have, because while the moon is turning around the Earth has to counter wobble.
Mm-hmm.
Yeah? So when we start with velocity 0, this is not in a resting frame.
Okay.
Yeah? So we would actually see what we had to do is we would have to move with, I mean, we take the ratio of these masses, yeah? And
The center of mass, right?
I mean, if you want the do we want to try it out? I never tried this. So we would have to put minus 1,200. So it's mass. So it would be like the mass of the moon divided by the mass of Earth, I guess. Yeah. So such that there is 0. I mean, if the moon has this momentum and the Earth has the opposite momentum, then the system has no momentum.
Mm-hmm.
Yeah. So now I never tried this. Let's see. Okay, so you see the increase that we had here before. So let me do this again. Yeah. So I put this here to 0. Where am I? Okay, I put this to 0, and you watch this here. That is now wobbling, but previously was increasing. Yeah. So you see this is increasing, and now if we go here and do this again, unfortunately, I don't know why we see the same picture.
It has to refresh. That happened the last time, I guess. Right?
I have to zook. This happened the last time. Animate scalar. Did I? Okay, I don't know why we don't see it here, but wait. I have the 0 in here. So I'll take the 0 out, yeah. I go here. You see, yes, now it works. Now we have it. We have it compensated, and now we have the system going in this nice way. Yeah. Okay. So, okay, this is the now it's yes. So previously without it we saw it moving. Now it does not move. I have to because I'm potentially using this next year again. I'll remove this here in order for our future students to learn the same thing. Yeah. So I remove it, going back to this, and here you see that it's actually moving onwards. Okay, last thing for today is seeing this increased, and we do this now by Sun, Earth, Moon. And we leave the other planets out, but we also could, then it's basically the same thing. So we want to automate everything as much as possible, right? So say we now have an n-body system. Okay, 3-body system is this Chinese 3 sun. Yeah, an n-body system. And this we can now here do like this. So we have the potential energy, yeah. So we need to build our pairs of bodies, yeah. If you build pairs of bodies, then you're always in danger to use this, you'll have, so what you need to avoid is to build pairs twice.
Yes.
Yeah? So the way you can avoid to build pairs twice is like this. You make an outer sum, I equal to 1 and to the number of bodies that you have, and then you always said that the one that you've already taken in here is kept out. So you make the j being equal to I plus 1. You start from I plus 1 and go to the same end. Yeah? So the first one will be paired with the next two, and the second one will only be paired with the third one, right? And then you'll have this, and here this is also, you do the sum over the kinetic energy, you do the sum over all these bodies. And you see now the advantage of having this index here, yeah, because we can write this down in index notation, and then we simply sum over that index, yeah, and get as many kinetic energies as we like. So, and then here very simple. Now also here, we want to count this up, and I mean one function that you will always use in Mathematica. I'm in the wrong place here. Wait, something went wrong. So one thing that you will always use is this function. Why don't I see myself? So the function table, yeah? So table will give you, say, II, so you can count II from 1 to 4, say, yeah? So the thing is you can do here some So, I mean, this is a very useful function that you use, that you need a lot of time, yeah? Like, you generate a table of something which you specify down here with a start parameter and an end parameter. You can, yeah. So there are a few more possibilities. You see that you can also, for example, JJ, so you define more 5 to 8. Yeah, so you actually now get a list inside lists, because you have here two indices, and if you want to have this in flat, then again you use flatten that one. By the way, if let's do something else. You write flatten and put it in brackets. So if you have written a function and you don't want to go backward, you can you want to apply a function to your outcome, then you don't need to necessarily to go back. You also can write everything at the end, and by / flatten, yeah. And this is, for example, also a position where you can apply this lambda functions, say so for example you can do, I mean this will just now, apply everything to, I mean you can, if you have something and you want to take this, I mean this is maybe it's stupid, but say you want to take the square of something, then you can write / behind this and get the square of the thing. So square is actually, okay, this is there are listable functions and non-listable functions, and square, so if you take the square of a vector, you don't get a scalar product, yeah, because it interprets square as a listable function. So listable functions are applied to all the elements of the list.
It's the square of each.
So yeah, you see we ended up with the square of each element.
Yes.
Yeah? So they're listable and non-listable functions. Okay, this is not what I wanted to say now, but it just came up. Yeah? So, what did I do? We have 1 minute left and one slide left. There's moon. Where was this? I don't. Yes. So we get all the equations of motion. Yeah. Now this. So all we need to do is mass 1 is now the sun. Yeah. The sun is pretty big, so therefore we did not compensate for the momentum of the system, but here we don't see a lot because the sun is pretty big, yeah. So, and compared to Earth and Moon, we simulate this for 3 years. We have to, okay, what may be interesting? The only thing that may be interesting is how we put the moon, yeah, because the moon is in the coordinate. We know the behavior of the moon in the coordinate system of the Earth, right? So P2 is now the Earth, where we give a position, that the distance from the sun, and the velocity. For the Earth is roughly like this, 300,000 meters per second, 30,000 meters per second. And then the velocity, so what is the velocity of the moon? The velocity of the moon is, because in the system of the Earth, it's the velocity of the Earth plus what we had before. Yeah?
Yes.
So, and the position, the same thing. The position of the moon is the position of the Earth plus the distance of the moon and the Earth. And then again, flatten everything and run this for 3 years. Yeah. So, and these are kind of these equations of motions that drop out, and this is how everything looks like. I guess potentially, did I stop this? No. So you see, I did not write, I covered this, so you can figure this out yourself. This is a closed, so you can go to cells and this cell property, their cell properties, editable, and there somehow is that it is closed. Develop, deployed, convert to format, insert. Okay, so I'm actually hiding, yeah, the program, yeah, by closing, by keeping this cell closed. So if you want to know how it's done, you have to find out how to open it, yeah. So the same thing here. Now I'm just plotting. I've taken out just the Earth and the Moon to actually see that the Moon is still moving, because this is what we didn't see on the other slides. Okay, so this is what we had for today, and this kind of finishes a little bit our example of Euler-Lagrange equation. Yeah. Let me see whether I'm able to stop this.